Hello everyone, this is Sri again, the coordinator of PICS Today webinar series. It's my great pleasure to welcome you all on behalf of CoE-CPPICS IIT Madras. I'd like to extend my special warm welcome to Professor Jose Kapmani. He is from Politecnica Valencia University in Spain. He leads Silicon Photonics Research Lab there. Professor Kapmani will be talking about analog photonic computing. Before having this exciting talk, I'll request Professor Vijay Krishna Das to introduce our honorable speaker. I'll also request Professor Sudarshanan to moderate our Q&A session. Over to Professor Das.
Yeah, thank you, Sri. It is our really pleasure to little bit customarily we have to introduce. I think, in fact, I think we don't need any introduction for Professor Jose Kapmani, but for the completeness, I want to read out some of his accomplishments. He is actually full professor in photonics and leader of photonics research lab in the Institute of Telecommunication and Multimedia Applications, Universitat Politecnica de Valencia, Spain. So his research is having more than 600 research publications. I repeat, more than 600. This is an astounding number. And he also serves a technical program committee in ECOC, European Conference on Optical Communication, and of course OFC, well-known conferences internationally. And he is also fellow of Optical Society of America. Now it is Optica, and IEEE. And he also achieved various awards. I can't, there so many numbers, I can't list them. I think already we have given in the biodata some of his awards and accomplishments. And he also served as an associate editor in Photonics Technology Letter, IEEE Journal, and IEEE Journal of Lightwave Technology. And currently he is editor-in-chief in Journal of Selected Topics in Quantum Electronics. It's one of the prestigious journal for quantum electronics. And apart from academics, he is also co-founder of VLC Photonics, which is, I think, in 2020 acquired by Hitachi High Technologies. And then iPronics, that's a programmable photonics. And so you can imagine he is very busy, and in spite of his busy schedule, he has kindly agreed to give this webinar, to give time for this webinar, and also agreed to interact with our students. I think that was a great gift for us. And I suggest all the audience participants, please utilize this opportunity and put up a lot of questions. And he agreed to extend his question and answer hour for another half an hour or 1 hour. I think that is possible for him. He is agreed because he likes student. He's a good teacher, I heard. And you can put up your questions by clicking just right bottom corner. There are 3 dots, and then you click, and then you can get a Q&A icon. And there you can type your question and answer. In the panel, we have our moderator, Professor Sudarshanan Srinivasan. He will handle the question and answers. And also we have the our CPPICS CTO Arnab Goswami and moderator, coordinator Sri. And with this, I invite Professor Jose Kapmani to take over the stage, the platform. And I just want to add one more thing. In spite of his busy schedule, he has given kind support letter for establishing our Center of Excellence, Center for Programmable Photonic Integrated Circuits and Systems. And that helped us a lot for getting funds. And also we'll be looking forward for long-term collaboration with him and his group. And yeah, with this, Professor Kapmani, please. Thank you very much. Yeah.
Okay, thank you so much. That's a very kind introduction from Professor Das. So I appreciate also the prior introduction. And first of all, let me say, for me it's an honor to be here because Right now, programmable photonics is an emerging technology, and well, it's starting to appear in many conferences, but we don't have so many chances to spend 45 minutes, 1 hour talking about this this topic, which I believe is very important, and it's called to make a big change in the way that photonic integrated circuits are designed and employed, just in the same way as programmable electronics was a groundbreaking achievement in electronics. So today, I'm going to talk about one application of these circuits, which is analog photonic computation. So right now, I'm going to give you an overview of my talk. And here, what I want to say first of all is that my colleague Daniel Perez gave a prior seminar, and you elaborated a bit on the technology and about what is programmable photonics as a hardware technology, and what are the design principles, the constraints, and issues about scalability, etc. And of course, no technology is useful if you cannot find applications for that. So, of course, you can do a lot of things with integrated photonics, and most of them are directed towards I call signal processing. For me, signal processing is a technique to process waves, while computation. For doing computation, you need to define a unit of information. So you can think always about signal processing as a particular part of computing. So having said that, of course, integrated and in particular programmable integrated photonics can give you a framework to do a lot of very interesting and exciting signal processing applications. But it also opens the opportunity or the path to consider new concepts. And this is what I'm going to talk about today. And what I'm going to show is the result of almost 2 years of work, which we will now try to publish. We didn't want to do that until we were absolutely certain that there was a solid background to what we are going to tell today. The second thing I want to say is that this is not an individual work, although I am presenting here, I'm the presenting author here. This work is the result of individual efforts, a team effort, mainly by my colleague Andres Macho, who is a postdoc at my university, at my group, Daniel Perez, who you already know, and Professor Jose Azaña, who is a well-reputed, well-recognized expert in optical signal processing. And he is in Montreal, in Canada. Okay, so let me first of all go to what I'm going to talk today. I'm going to try to put into context analog photonic computation and why do we need it. And this entails also addressing a bit of the challenges that not only this particular way of computing, but in general, integrated photonics and programmable photonics need to overcome in the next years in order to circumvent a current limitation that electronics is facing. So that will lay down the basic context and the basic aspects of, so I can proceed then with the new proposal of analog photonic computing. So in analog photonic computing, I'm gonna provide a very broad introduction, and I will specifically emphasize several points which I think are very important in any computation theory in general, but in particular in this one, which is new. That means the definition of a unit of information, we need that if we want to do computation. The definition and the analysis of what are the blocks that we are going to use to process this unit of information, which we call gates, in parallelism with, let's say, digital electronics, although what I'm going to talk about has nothing or very little relationship with digital electronics, but we want to keep the terminology so it's understandable. And then we want to, I will talk about how to design a little bit more complex subsystems from taking the gates as starting points. And that entails doing what we call feed-forward or combinational subsystems. That means systems where the signal is going to go in a given direction, let's say from east to west or from west to east, if you like that. Combinational subsystems where, as with Boolean logic, you allow for some kind of a feedback signal. And this will provide quite a complete setup of this new way of doing computing. All through my talk, I'll be stopping at the view graphs and providing some comments and extra notes, which you will not find in the view graphs for the sake of simplicity. Otherwise, we would end up with crowded view graphs. Okay. Finally, I will try to make a comparison between this computing approach, what it brings as unique, and other computing paradigms like digital or quantum. Okay, and then I will summarize and conclude my talk. Okay, so first of all, of course, in 45 minutes, I will, or 1 hour, I don't have time to cover all the subject. But fortunately, we recently uploaded a reference material. It's a quite long paper. I can, I warn you that it's a quite long one. But you will find the details of what I'm going to present here in a very, very developed way in this paper, which we uploaded into archive last week, because we wanted to have it ready for this lecture so you could use this as a reference material. Therein you will find, as I said before, the detailed descriptions of the main concepts that I'm going to describe today. Okay, so let's start with the context. Right, the context is the following. We know from our daily experience that there are many applications in information and communication systems that are demanding ever-increasing computing and signal processing power. I just put on the logo of some of them, which you would find familiar, like 5G communications, the Internet of Things, neuromorphic computing, mobility, and sensing, etc. And so far, this demand has been very well served by electronics during the last 5 decades. Electronics has had a tremendous development and has been very successful in coping with these ever-increasing computing and signal processing demands. And I said ever-increasing because they are not stopping and they are not going to stop, because these applications are going to demand processing power, and others will come that will require extra. Now, electronics now is facing some saturation in their scaling laws, and probably most of you are familiar with Moore's law on the integration density of transistors. There are all other laws which probably are less well known, like Denner's law regarding the power density of integration. But most of them, as you can see here, are facing some kind of saturation. You may read that, okay, we are going down into 2 nanometer electronic circuits, but then at the same time, you put more transistors, but many of them have to be switched off. And the same thing happens with the clock frequency of computers. And of course, some solutions have been proposed relying on multi-core computing. But then again, there's Amdahl's law, which actually shows a clear saturation path. So that's one thing. And on the other thing, digital computing is probably not the most efficient approach to some applications that require maybe real-time or multilinear analog operations. And we know that, for example, because neural networks and neuromorphic systems are starting to be very successful because they are actually doing a different way of computing. That's not the traditional von Neumann digital computer architecture. So we have this context where we need other technologies to complement electronics in order to boost our computing power. So on that side, these new technologies that are not particularly digital electronics and these non-digital computation approaches are being now the subject of intense research. What I show here is a kind of different summary curves where you can actually see the different approaches that have been proposed in the last years. And you go from the very most conservative approach, which is called more Moore, where actually the rationale is to keep on with the digital electronics paradigm and try to improve our means of integrating transistors by 3D stacking or by using other kind of approaches like dark silicon, etc. Then you have another approach which is focused on investigating new materials, new approaches, but yet still connected with a semiconductor technology, like silicon photonics, like 3-5 materials, probably carbon nanotubes, etc. And then you have a more disruptive approach, which is on the third axis, which is called Beyond Moore. And that way to work, or that area is focused on developing new models of computation. And there you can see, of course, the very popular neural-inspired computing, the quantum computing, which is right now a hot topic. But of course, you have other approaches like classical analog computing, etc. On the other hand, you can see a prediction of different technologies and different approaches for doing computing, which build from the von Neumann program type paradigm and what are the expected progress to be reported in the next years, but also other approaches which, although still rely on digital CMOS circuits, are non-von Neumann type or analog, and on top of that, quantum computing. So you can see there a summary of what is expected to be reported or developed in the short and medium term, and what you should expect to have in the long term. Okay, programmable photonics sits probably in the medium term right now. So actually, this is a good opportunity to start working on this and start building these beyond Moore approaches. So that's the challenge that we have. And we have the technology of optical integrated optic circuits, and one can think about doing something about that and developing these new computing paradigms. Okay, so integrated photonics as a technology is ideal because it is complementary to electronics, can be integrated on chip, and is CMOS compatible. So to solve the hardware problem that we have in programmable integrated photonics is the right technology because it brings potentially the desired features that we want for this complementary technology to electronics. It's not going to compete, but it's going to complement it. And regarding the second challenge, developing new computing paradigms, of course, there are people working on quantum, there are people working on neurophotonics, but we can also think about a new approach that is actually suited and especially suited for programmable photonics. And this is what we are going to talk today. And this is what we call analog photonic computation. Okay. So that's the basics of the introduction, okay, to the subject, right? So nowadays, like I said, if you want to do some computing, you need first of all to define a unit of information, and this is what we call the analog bit. The analog bit, or in short term, we contract that and we call it Ambit. It's we propose it to be a two-dimensional analog function, and here we encode the information in the modulus and the phase of each of its two components. So the analog bit, the Ambit, as you can see here, is made of the superposition of two vectors. Okay, it's a vector, but each one there's an amplitude qualifying each one of the two orthogonal vectors. And we can use many ways to encode it. Okay, how do we encode these two vectors? Well, the simplest way to do it in integrated optics is to use a similar approach to that of the dual rail approach that is employed in quantum computing. In this case, actually, what we do is we use a one waveguide to convey the modulus and phase of the first component, and another waveguide separately, especially convey the modulus and the phase of the second component. So to transport this information, we can think about long pulses, or let's say photonic pulses, and or other kind of artifact. But here, the important thing is that we are going to use the same spatial mode in each waveguide, so it would be probably T mode, and the spatial characteristic is not changed, it's only the envelope, the time domain envelope that is employed, and it's the amplitude and the phase of that envelope is the ones that will carry the information of the ambit. So this ambit is like a two-dimensional entity, if you want to call it like that, and in that sense, it's not very different from what you have in quantum computation. Of course, photonics gives you a lot of ways to encode the information, and we don't really need to use that if we don't want. But for practical reasons, the one that we think is the most adequate right now is the one that I'm showing here. Nevertheless, we can realize it in different ways. For example, we can use different guided modes in a multi-mode waveguide, as you can see here. We can use a single mode waveguide and employ two orthogonal polarizations. In this case, actually, this is practically possible, although in some integrated photonic platforms, which usually propagate one polarization state, that becomes a bit complicated because you need to duplicate your structures. You could use probably the same spatial mode, but different frequencies or different wavelengths or colors if you want to do like that, if you want to think about that. And finally, you can, of course, do time multiplexing and allow for a given slot, time slot, for the transmission of the amplitudes of this ambit, and just reserve one part of the duty cycle for one of the components and another one for the other component. So these are the approaches that we have, and these probably can all be implemented with more or less difficulty in integrated photonic structures. Right. How about the detection? We are saying that the ambit has two components, and they are two complex valued components. So each one will carry a modulus and will carry a phase. So we were able to detect the ambit. This is a very basic scheme, of course, with a coherent detector. Then we would be able to completely retrieve the 2 degrees of freedom of each of its components. So actually we would have 4 degrees of freedom. However, as you know, coherent detectors are usually costly, and although they are mainstream right now in communications, and probably they will be for other applications in the next years, is direct detection, which probably is better suited now in economic terms for detection. In that case, what we are able to retrieve is actually the amplitudes of the two components and the phase difference between them. So we are not able to recover 4, but 3 degrees of freedom. And of course, the state of one can think about how to represent this ambit by using a representation which is very close to the Bloch sphere in quantum communications. The only difference here is that while in quantum communications we are always forced to have modulus 1 qubits, and of course we would use a Bloch sphere that you can see in the inner part of the figure, the one with a stronger blue color. Then in our case, we are not restricting our ambit, our unit of information, to be modulus 1. It can have a power, an overall power, which is different from 1. And of course, this entails using a sphere with a different radius. But the way of representing this is basically the same as in quantum computation. So you can use the 3 degrees of freedom, which would be the power, the radius of the sphere, and 2 angles. That's actually the way we represent that a given ambit. And of course, that reminds very much to the quantum bit, but there are differences, as I'm going to show now, because when you actually represent your qubit, you know that you are entitled to cover all the Bloch sphere, but when the detection stage comes, then you have to collapse the wave function, and then actually at the end of the day you will have a 1 or a 0 value. That doesn't happen in quantum in APC, in analog photonic computation, because you have access to the whole sphere, and moreover you can detect any after you detect the ambit does not go to 1 or 0, but it can go to any part of the sphere. So that gives you a very powerful analog encoding system. So what is the roadmap for developing this quantum theory, this classical theory? First, we need the unit of information, which we have defined. And afterwards, we need to define the processing units, the gates. I'm going to spend some time with defining the gates right now in the next minutes. And from that, which are the basic building blocks, I will, in principle, be able to construct or build more complex circuits. So from basic gates, I will be able to build blocks that are either combinational or sequential, like it happens with electronics. So one important thing is to define the concepts, and the second and very important thing is that since we are saying that this can be implemented in integrated photonics, in programmable integrated photonics, the next step is how do we translate those architectures into an implementation in a photonic integrated programmable circuit. Right, and then again, we will have sequential and combinational or feed-forward and feed-backward circuits that you know. Once we've done that, the roadmap will be completed by constructing more complex systems where you have gates that can process not a single ambit, but multiple ambits, okay? Construct more complex parallel computing architectures, develop algorithms for that, and develop an information theory for this computation, this particular approach of computation. So this is the roadmap. And right now, I would say we are actually in this part. We are defining these architectures, and our next step is to materialize those architectures into programmable photonic circuits. Okay, so let's start with the gates. Okay, the processing units. We have defined our input, our ambit, our unit of information. We have said that there are many ways of encoding, but we are going to select for this talk the dual array. So actually, the two amplitudes of the ambit are shown here. You can see that on the left-hand side of the view graph. So the ambit gate is a device, an integrated optic device that is going to take these input ambit, which is represented here in the block square, and is going to take it somewhere to another place. Okay, so it's going to produce an output ambit as a result. And there are different ways of implementing these gates, and the degree of refinement depends very much on what your technology is going to allow you to do and what assumptions are you going to be able to do. I'm saying this because in quantum computation, one usually assumes that gates are going to be unitary, which amounts to assume that your systems are lossless. And you know that this is not true. But you can build a computation theory based on unitary gates, which resembles quite a lot to what you're going to achieve in practice, provided that if, for example, you use an integrated photonic circuit, your losses can be very low. And this is one of the reasons why for quantum implementation, one usually resorts to low loss technologies like silicon nitride. Well, actually, for unitary gate, you can build an arbitrary unitary gate by cascading 3 rotation operations through along 2 different axes. I'm showing one very, very simple example here that is reported in the paper, and this is in the upper part you have a matrix that represents this cascade of 3 rotations. Okay, so it happens that in nature a rotation around the Z axis can be implemented with a couple of parallel phase shifters, integrated phase shifters. And a rotation around the y-axis can be implemented with a 3 dB balanced Mach-Zehnder interferometer. This is shown here in your lower part of the view graph. So as you can see, we can implement an arbitrary unitary gate quite simply using drawing from standard integrated optic components. So that's perfect. That's very good. There are other options that we studied last year, the different options about doing the rotations around other axes, and usually they turn out to require more components. But this implementation is not the only one. You can resort to more different implementations. For example, here you can think about rotating around, doing the intermediate rotation around the x-axis instead of the y-axis. And then actually what you need is a directional coupler. Okay, you can find details about this in a paper published in Lasers and Photonic Reviews, which is included in the reference section in the archive paper. So first message is that the gate implementation is not unique. Okay, so because it is not unique and we are constraining integrated optics by footprint and by losses, etc., then we have to choose those implementations that render the minimum number of components. And these two that I've shown you are probably the most compact ones. Yeah, but then again, we are thinking only about unitary gates, and the truth is that in the real world, matrices are not going to be, the systems are not going to behave really like unitary gates. There are losses, non-uniform losses, and that will prevent our system to be unitary. We can construct the computational theory from these unitary transformations, no problem. This is done in quantum, so it can be done also here using this model. But if you want to go a little bit further, you can account the losses, and this will lead to non-unitary gates. But the nice thing about this, the good news about this, is that these non-unitary gates, which will change the modulus of your ambit after propagation through the gate, can be modeled using or can be implemented using unitary gates and also diagonal gates, diagonal connections. And many of you might be familiar with this, because this is what is called the singular value decomposition problem, and that tells you that you can take an arbitrary matrix and decompose it into the product of two unitary gates surrounding a diagonal matrix. Okay, two unitary transformations surrounding a diagonal matrix, and that allows us to define a way to implement what we call the general gates or the matrix gates. General gates are gates that are reversible, but they are not unitary. And M or matrix gates are these 2x2 matrices which are not reversible. Okay, so actually we can use this very simple scheme where we sandwich in between the unitary gates this diagonal matrix, or this implementation of a diagonal matrix, which only takes into account components that can be either amplifying or just losses. Okay, so actually the operation of the general gate actually changes the radius of the input and output sphere. You can see the evolution here, how your system actually comes from an input state, which is on a sphere with a higher radius, comes down to a sphere of a smaller radius. Okay, but if you can reverse this transformation, if you go instead from left to right from right to left, then you will be able to recover your input state. The M gate is different. With the M gate, you do the transformation on one side and you are not able to come to backwards to the starting state if you do the reverse operation. And that reminds very much to what happens in digital electronics. All right, so these are the three options that we have for the gates, and there are no more than that. This is the very basic AND-bit gate. And from that, we can build different subsystems, which can be more or less complicated. I'm going to start with the combinational subsystems, okay? So one of the different things between this analog photonic computation and quantum computation is that we are able to have fan-in and moreover fan-out gates, okay? Fan-out gates are not possible in quantum computation, as you know, because they are forbidden by the non-cloning theorem. So actually, one can use the gates that I have defined before, and you need to take into account that when we are talking about fan-in or fan-out gates, we are always either wanting to combine ambits or we want to divide ambits into different outputs. The general picture of the general description of a fan-in gate is the one that you have on the upper left-hand side, where you have two different ambits, and the two outputs will give you a weighted sum, and a weighted difference. In many applications, you just need the sum, so you would not need the lower port. And in the case of the fan-out gate, actually what you want is to divide a given input state into two outputs. And you have this representation here where you have a psi, an ambit which is characterized by psi, for example, by psi state, and you want to divide it into multiply by n into one output port and multiply by m into the output port, into the other port. The way to do this is to actually you need to use different gate configurations, but one way to implement this is shown in the right hand side of your view graph. I don't have time to give all the full details, but you have them in the paper. The interesting thing about this is that these internal blocks that you see here can be integrated with implemented with standard integrated photonic components like MMI couplers or directional couplers and phase shifters. What you have is a fan-in or fan-out, in this case, input fan-in combination of two different ambits, which you have on the left-hand side, and you have the different options for the combinations on the right-hand side. Depending on what actually is the output that you need for further processing, you would choose a couple of output ports or another, okay? These numbers N and M can be programmed on your photonic programmable chip, so you are always free to set M or N to be 1 or 0. That's always possible, or you want to have like a division. So this is one thing that can be done, and this is a very basic building element for constructing sequential systems, combinational systems, but also sequentials, as we will see later. Here you have an example where actually what you can see is a very simple example of a multi-ambit combinational architecture. And this is actually, you can see here that we have two input ambits, okay? So they go into a fan-out and to a couple of fan-out elements. And for a fan-out to give you a perfect division of your input ambit, your second input has to be a zero state, no input. So you guarantee that your ambit is evenly divided here into these outputs, and the same thing happens here. And of course, you can always think about then combining your outputs because you have fanning elements that can combine you the components from one of the dimensions and the components of the second dimension. So that would be a very straightforward combinational system. And of course, these matrices are arbitrary. So you can always choose what you want to do over your, what operations you want to do over your ambits. You have to complete freedom then to manipulate the amplitudes and the phases of each of your ambit components in this case. So that's an example. We are working right now in optimizing these circuits so they can actually be employed in different computation tasks. Right. We can always go to more elaborate designs, and this depends very much on how are you going to factorize your operations. We're working with matrices, and you know that there are a lot of different possibilities to factorize matrices. And of course, we can, let's say, we can think about different alternatives. What I'm showing here is an example that is developed in the paper that allows you to actually implement any arbitrary M gate using Pauli matrices. This is based on this algorithm, on this factorization algorithm. And also remembering that the standard Pauli matrices are connected to the rotations around the X, Y, and Z. And these again are connected to very simple integrated optic components. So this is actually one way to implement your arbitrary M matrix, M gate. It's a little bit bulky. So one of the areas of research right now is how we can actually design procedures in order to get the simplest versions for the different matrices that we the U, the M, and the G that we can need on the circuits. Another option is to implement control gates. And those of you who are familiar with quantum communications, then it's easier for you to understand the operation of control gate, but actually transforms a given input. In the case of quantum communications, computing transforms you the input state of a qubit depending on the state of a control bit. Well, here you can do the same thing. You can actually use a control ambit to control the operation of a matrix or a gate. So actually this transformation is only active when this control ambit has a certain value. So one of the nice things here that you can do in photonics, but you cannot do in quantum communications or in quantum computing so easily, is that we have two options here. You can implement the control qubit, the control ambit, sorry, electronically, or all optical. Okay. So the all optical is not very interesting because actually the control ambit, as you know, is only being employed to enable or disable the gate. But remember, if you listen to Daniel Perez lecture, is that in the gates in the programmable photonic circuits are activated by means of electronic signals. That means electronic currents or voltages. So you can always do a mapping from your control bits, your control ambits, to your input electrical ports and actually enable or disable the transformation that you want to implement through the control gates. Of course, you have different examples. You can have implement any kind of control gates that have been reported in the literature. Here is an example of a control node where your transformation is implemented internally in the photonics by a Pauli sigma X matrix, but it can be any other transformation, as I said before. You can do a control node gates that are called Toffoli gates, are also quite famous or quite employed in the literature of quantum computation. And again, you can do the control electronically, and this is a very big advantage. Okay, your control signals are classical. They are not. You don't need to resort to the fact that you need to be assured that you have a quantum state there. So that allows you to save a lot of resources in terms of garbage bits. Okay. And this allows you to do this kind of transformation. So remember, for combinational systems, you can do the standard matrix transformations, but you can also do control gates. And moreover, you can have fan-in and fan-out gates. So the second option is the sequential systems. Here, what we are going to allow is for some feedback to happen inside our computation circuit. So we start with an input AND bit. We get into a very simple circuit. This is just for one AND bit, the simplest sequential circuit that you can think about this. And this is this is easy to this is actually processed by this fan-in. So you will have a actually your input here, okay, and it will go into a transformation, and then you have a fan-out. So the fan-out is actually, as I said before, and you can see in the paper, if your other input is a 0 state, there's no signal here, then you will have this signal divided evenly or with a required division factor that is given by these two numbers, one part going into the output, one part going into a feedback loop where the signal can be further processed by another gate and combine in the fan-in input with this. So the equivalent transformation that you are emulating here, it's the one that you have here. We're still exploring the applicability of these sequential systems, but one important application here is like in Boolean logic, where you can use your your sequential systems to emulate combinational systems using a reduced number of components. Okay, that's one of the advantages. Of course, you can always think about this feedback path as a kind of memory. So this, in principle, will implement some kind of memory within the computing system. So you can find, or you can think about more difficult or complex example. I don't want you to go into the equations here, of course. This is too complicated. I wrote down just for reference. And the thing about this circuit is that you can compute the transformations between the input and the output AND bits. And of course, you can get a linear relationship between those two input and two output bits that can be modeled through complex matrices. And interesting topic, or the interesting thing about this is that in particular, and this is shown in the paper, this circuit is actually equivalent to the one that we've shown before to illustrate the combinational system, which I show here. Actually, it is shown in the paper that your circuit on the right-hand side is completely equivalent to the one on the lower-hand side. But the difference here is that while in the right-hand side you have 6 elements, here, you have 4 different gates. Then here you only have 2 of them. So this tends to show also that what I said before, that by using sequential systems, apart from the fact that you will allow to have feedback and more rich processing or computing capabilities, you will be able to save in the number of gates and number of components. So right now we are exploring the theory of these sequential systems, how to optimize them in terms of number of components, how to adapt them so they can run different processing and computing algorithms efficiently. And finally, I would like to summarize the properties of analog photonic computing as compared with other computing paradigms. So in this table, actually, what we have listed are the properties that you can implement with the digital computing, that is the standard Boolean computing, with quantum computing, with neuromorphic computing, and with analog photonic computing. Okay, so actually analog photonic computing can more or less efficiently emulate the rest or most of the other computing paradigms, with the exception of instantaneous non-locality, which is not possible because we are talking about the classical approach. But apart from that, it's very versatile because it allows you to do all kinds of computations, both linear and non-linear. I didn't have time today to talk about how to implement nonlinear computation with these gates, but you can find more material in of course, as I said before, in the paper. You can do both reversible, irreversible, forward and backward propagation, parallel computing, and other operations which are very hard or even not possible to do with other computing technologies. So the message here, and a takeaway message here, is that, I would like, this is of course a new paradigm that we will need to demonstrate that it works efficiently on photonic chips. I don't think this will be particularly a big problem. The big problem is how to optimize. So there is a lot of work on how to develop architectures and optimize them. So this is a very different approach to other paradigms, because either what you have seen in optical computing, if you have read papers on optical computing, are actually architectures that either try to mimic those of digital electronics, for which I believe that, and I think it's common consensus that optics is not very well suited for that, in addition to the fact that we don't have memories in photonics. Or on the other hand, the architectures are restricted to provide analog signal processing support to other existing computational models. And this is the case when we try to implement a quantum computation circuit with photonics, or a neuromorphic computing circuit with photonics. Photonics is an auxiliary technique here, and is valid, but it's not complete. There are elements that, even though you want to do a linear quantum computing, you can do the linear transformation, but there are other elements. You always need some elements that are going to be alien to photonics, okay? And in neuromorphic computing, many of the operations that you need to do, the thresholding functions or the thresholding operations, are so far being done either offline, or they require a conversion to electronics. Okay, so that's one of the takeaway messages. There's another takeaway messages who I want to summarize in this view graph. So with analog photonic computation, what we have is the potential to provide an evolution from optical signal processing to true analog optical computing. And with that, I am referring to the fact that we are not doing processing of waveforms, but we are doing processing of information units, which we have defined. The other thing is that we can implement them efficiently with programmable integrated photonics, because as you have seen, most of the systems rely on gates, which in turn are implemented by rotation transformations, which are done naturally by very simple photonic integrated components. The third thing I want to remark is that we are not developing this theory to compete with electronic processors. Electronics are digital and are great for that. And digital computation is great for many applications. But there are other applications, as I said at the beginning of the lecture, for which probably we can find more suitable approaches. This doesn't mean we can do them in digital, but probably with an overhead cost. So it gives an opportunity to create a new field of research, both in computation and information, because there's no, I will put you some example. I talked about the block sphere and the possibility of encoding states. And like you see, when you detect your ambit, you don't lose the information. You don't lose your waveform is not collapsed. The wave function is not collapsed. You can still conserve it because simply you can clone it. Okay. So you have access after detection to all the states on the block sphere. That is limited, of course. You don't have infinite states, but that's limited by the resolution and the errors that you will have in encoding your states. But provided that you can discretize that block sphere, then you have a source with a given for which you can compute your entropy and information power, etc., and develop this theory for this new computing, which is substantially different. We will not collapse to either 1 or 0. We have the whole sphere to encode information. That makes a big difference, because it is actually implementable with integrated photonics, and in as much as this technology will go down, and especially we are able to implement it with programmable photonics, we will be able to have these computing systems with a potential low cost and repeatable fabrication. And finally, a technology that will team up and help to unlock the limitations of digital electronics processing power, with the aim of complementing and not competing, as I said before. So this is all from me today. As far as the lecture is concerned, I want to thank you for your attention. And like I said before, like we said, I'm pretty happy to take your questions. Thank you very much.
Thank you, Professor. That's a virtual round of applause from me. Thanks for the nice talk. So Vijay, should I take over for Q&A now?
Yeah, please.
Okay.
Yeah.
So yeah, the floor is open for questions. I already see a few questions in the chat, and I would encourage those who want to type in questions, please use the Q&A box rather than the chat box. But for now, the ones that are in chat, I'll also include them in the order I've received them. So Professor Kapmani, the first one is from Avijit Chatterjee. Hello, Professor. Could you please explain more on what is the 3-axis rotation for unitary gate in practical systems?
Okay, thank you. Thank you for the questions. Well, when you explore the theory of 2x2 matrices, these matrices can be made isomorphic to 3x3 matrices. There's an algebra theory on that, and there's a direct link between the standard rotation matrices that you know in 3-dimensional geometry, and these two 2x2 rotation matrices, which are exponentials of the Pauli matrices. Okay, so actually it's too long to I don't have time to explain, and it's a very long explanation, by the way. But you can find it in the in the paper. There's a reference to a paper where that is explained. So actually, we call these rotation matrices because there is this one-to-one correspondence between these 2x2 and the 3x3 real matrices around the 3-axis. Okay, so actually you are maybe the question is, are we doing any physical rotation around the axis? And the answer is no. We are actually using the simil, the relationship. It's just a pure way of expressing things. Okay, so this is how would we say is a way of speaking and not and using the same terminology. However, there is a caveat here that has to be taken into account. When we go to the 3x3 matrix theory, there is a rule which is called the Euler rule that tells you, okay, if I have a point in my sphere and I want to go to another one which is actually arbitrary, I can achieve that by doing 2 rotations around 2 non-orthogonal axes. Sorry, around 2 different axes. Sorry, they cannot be parallel. Okay, so this is what we exploit, not the geometry, but the concept in implementing the unitary matrix. An arbitrary rotation around the geometric sphere is the same to say I'm going to be able to do any kind of 2x2 transformation, no matter complex value transformation, no matter what the values of the matrices of the elements are. So we draw back from the geometric model, the 3x3, and we say, okay, I need a transformation around X, a transformation around Z, and another transformation around Z. So I go and I do exactly the same operations, but with the 2x2 matrix. And this is done because the 2x2 matrix are implemented with very simple photonic components. If you want more information, like I said before, there is a whole theory that is was published last year in Lasers and Photonic Reviews, and you have that in the paper reference section.
All right. The next question is from Nagarajan. How did you define garbage and bit? Which parameters decides it's a garbage and bit?
Okay, that's an interesting question. Okay, garbage here has a different meaning than in quantum. Okay, in quantum computing, the garbage ambits, the garbage qubits, usually you need to inspect them because they provide you information, useful information, critical information that the system that you're trying to emulate or you're trying to implement is actually working as it should. If you are doing your operation and then you inspect the garbage and the garbage are okay, then you know that the output is actually the processor is working correctly. Here, the garbage ambits are usually due to the fact that we use symmetric and reversible systems. Because we use symmetric and reversible gates, sometimes we will not need some of the output ports. So the information of these output ports for a particular operation and at particular time can be considered as garbage. It doesn't mean that they are going to be garbage. You don't need to examine them. Okay, these are true garbage. So you don't need. It's not like when you have the ancilla bits in quantum computation that I mentioned before. So it depends on how you are actually programming your system at a particular time, that some output ports you don't need them. You need the information from several output ports and not from others. And those others for which you don't need the information, they can be considered for that particular application and at that particular time as garbage.
All right. The next question is from Kumar. An earlier paper in Nature 2017 from your group demonstrated the basic quantum gates CNOT, SWAP, Hadamard from the 7-cell hexagonal mesh and from the feed-forward mesh design. How do these basic unitary gate designs discussed now different from the earlier designs in terms of functionality?
Okay, that's a very good question, and it is connected to the fact, if you remember in the lecture, I've said that the way to implement the gates is not unique. You can find different ways of implementing the gates, and actually, the one of the works or one of the open research lines that we have to do is to really get the designs that really require the lower or the lowest number of components. Okay. A transformation is linear transformation is no more than a matrix transformation. So there are different ways how you can compute this. You can either say, okay, I'm going to try to do the full transformation as a n by n matrix, whatever it is, and then implement that with your programming the elements of your of the matrix, and then turning the bias currents to the phase shifters in the waveguide mesh, so they implement that. And this is what was reported in the 2017 LPR paper, or the Nature Communications. Yes, sorry. And this is one approach which is completely legitimate. You can do that. There's no problem. What I'm discussing here today is a little bit more structure. What I'm saying here is that we are building from 2x2 gates. So I'm actually using these 2x2 gates as the building block, the basic building block to build other more complex blocks. I didn't have time today to say how can I go from a 2x2 block to an n by n block, because there's no material time here, and we are still working on that. But it is another way of doing this approach, which has the advantage of being a little bit more rational or more logic, because you work with smaller building blocks and you end up building more complex circuits. But both of them are okay. We still need to know which of them is more effective. Okay.
All right. The next question is from Yesh. Can you clarify the fact that we use non-unitary nature of gates due to loss or gain to implement fan-out gates, which is fundamentally different in quantum computation, as in which won't be possible in quantum?
I think I understood the question. How can I use the non-unitary gates? Sorry,
No, I think he is trying to, again, it's sort of an extension of Kumar's question. I think he wants to understand how do these gates differ from the quantum gates, right, in quantum computation? And is it the fact that you have these non-unitary gates to implement fan-out with loss and gain, is that the real difference between the two?
Yeah, that's one of the main differences between this APC and quantum computation. First of all, the transformations do not need to be unitary. Okay, you can still build your algebra and your theory without non-unitary transformations, and this is not allowed in quantum, because remember that at the end of the day, your input and output state have to have unity. You have to be unit modulus. Okay, so you have to either renormalize or do whatever operation it takes to comply with that requirement. We don't need that in APC. Okay, because remember that our block sphere doesn't need to have a unit radius. It can have a different radius. Okay, that's one difference. The other difference, and that's very pointed quite rightfully here, is that here we can implement a configuration that, because we are using classical signals, will carry out the task of doing the cloning, or if you want to call it like that, the fan out. Okay, if you were to use this structure with a quantum bit, it will not work, because in this case, remember that that you are restricted by the laws of the non-cloning theorem, so you cannot clone it. Basically, the way that the quantum state is conceived and is prepared prevents from the cloning operation. So actually, it's in the state, rather it's not in the logical circuit, but it's in your state. But it's going to prevent you to do the cloning. So actually, the state will go into one port or the other. You know, it cannot go into the two.
Okay, thank you. So the next question is from Shrikant. Will this replace optical signal processing in due course? And also, will it replace digital signal processing, or even pure analog or digital signals used in devices?
Okay, well, in my view, the answer is no. I said that signal processing can be considered one part of optical computing. Okay, so the computing can be employed to do this kind of manipulations over information units, the ambits, for example. But signal processing, where, for example, you would need to filter a signal, is rather different. You want, like I said before, you want to process the wave characteristics. You want to take out frequencies. You want to add extra phase. You want to chop a signal. You want to delay it. You want to do things over the waveform, but not over a unit of information where you store your information. So I would say it will not replace, it will complement optical signal processing. It will not replace digital electronics. It will complement digital electronics, because this is a way of computing that is purely analog. So I don't think it will replace it at all. It will complement electronics, but we believe is an efficient way to use optics for computing. Okay. In this case, think about computing as a more general paradigm of something that treats units of information, and that unit of information doesn't need to be the digital bit of electronics.
Right. All right, thank you. So the next question is from Navdeep. Thank you for the great session. Like in silicon chips, we have fundamental limitations on size. Are there any limitations in photonic processing, like in making of photonic field programmable photonic gate arrays?
Okay, thank you for the question. Yes, indeed they are. Yes. First of all, think about if you make a comparison between the minimum processing unit of electronics and photonics, you will see that your transistors can be very small. They are in the nanometer scale right now. Okay. While if you want to put it like that, what is the equivalent processing unit or processing element for photonics is a phase shifter. Okay, so it's a standalone phase shifter, is several hundreds of microns, not nanometers. It's much bigger. Okay, so that means that you cannot compete with electronics in terms of footprint. Okay, but at the same time, electronics needs to work digitally, while in photonics you can do the processing, it can be analog, and that means that you have a lot of power for doing processing and computing. Okay, so just to give you an example, if you want to implement a digital filter with electronics, then you know, first of all, that you need to sample your waveform. Okay, you have to first sample, then you have to digitize. Then you will get into your digital filter, and then you have to do the reverse operation. Then you have to, to recover your analog signal. This you don't need with analog signal processing. I'm not saying that it's better for all, but for this, you avoid many intermediate tasks that you do in electronics. So for some applications, analog processing, and I'm not going to say specifically photonics, but analog processing is more adequate than digital processing if you can afford that. And with optics, I think that you can afford that because optics is broadband and has a very low latency and very low losses. I'm not saying analog computing or processing is good in other technologies, because it's, for example, in electronics, sometimes it's very demanding, and it probably is not very broadband, or you need to change your circuit designs depending on the band at which you are working. You have reflections, etc. But in optics, it can work very well.
Okay, thank you. The next question is from Ashutosh. Is there any preferred photonic platform to demonstrate the mentioned gate operations?
Okay, that's a good question as well. I would say that in principle, in our case, the preferred technology is silicon photonics. Because silicon photonics renders quite compact devices, because it's a high contrast technology, and it sits in between silicon nitride is lower loss, but the devices are much bigger, the circuits are much bigger, and of course they are very low loss, but that is really only important if you want to do, for example, quantum, if losses are really killing your application. On the other hand, probably your next question would be what happens about the optical sources, and you need to compensate losses, etc. And for that, you need, of course, active active semiconductors like 3,5 indium phosphide. So right now, if I were to say something, is that in my opinion, the best approach is to keep all the passives in silicon, at least for computing, okay? And just use any kind of hybrid technique to integrate your actives. And there are very promising results. I think that Professor Das mentioned that you had a seminar from Professor Günther Relkens. I don't know if he took the opportunity to report his work on transfer printing, but the transfer printing is very interesting. It's definitely, in my opinion, the way to go, to use these coupons from indium phosphide and stamp them in the selected places on the silicon chip. That will allow you to keep on your silicon fabrication platform, your routines, and then usually also incorporate the active elements. So in my opinion, that's the best option, at least for computing for that.
All right. So that wraps up. Yeah, so I think we can move on to the panelists. So, Bijoy,
Yeah.
you have questions, so
I
you
just
can go
want
ahead.
to just follow up Asito's question there. So,
Yeah.
yeah, really, it's a very good talk and new area opening. I think I like it. That's a lot of work put up. So one thing is that my question is normally all the phase shifters in silicon photonic or silicon nitride, we go for thermo-optic phase shifter. So unlike electronics, I think here your switching operation is not so great, right? It would be very slow. So how fast this computation could be? Of course, parallel computing, I think it is one way you explained like a quantum things, it can be done. But every gate operation, it may take something hundreds of tens of microseconds. So, and again, if we put some kind of plasma dispersion phase shifter, then you are adding loss. So what could be the possible solution for that so that your gate operation can be faster?
Okay, that's a good question, and it's been on the spot for time right now, and I would say that if you were to you would need to classify your applications on in that sense. If you need to do processing on a basis where you don't need to refresh your phase shifters at a very high speed, but what you care about is the processing speed of going inside photonics, you are doing this kind of computing in memory, where you are actually leveraging on the speed of propagation and the low loss, and you don't need to refresh your settings at so much speed. Then thermo optic can be good enough, because there's good there it is slow if you compare, of course, with plasma dispersion, but at the same time, I think there's work in progress that is reducing, of course, up to certain limits the speed. I think that we will. I'm not working on that, but I think that we will see in the next years a thermo optic phase shifters with tuning speeds of below 1 microsecond. But we will not. Certainly, we will not reach the nanoseconds, the few nanoseconds of plasma. So, in answer to the second question, if you need some really fast refreshment velocity or speed, then at this time, I don't see any other option than plasma dispersion phase shifters. And like you very well mentioned, they are lossy, so that might require some compensation. But this has not been studied in the context of a very complex circuit, to my knowledge, at least.
And another, I think, since it is analog, and I think probably will it be good also for that we can go for like a WDM type, so that I can increase the bit and calculation just in the one more freedom we can get as a lambda. Same gate I can operate with two successive lambda, closely spaced lambda, or 2 or 3, 4, and so on. And then we can again demultiplex, and I can serialize the data. That way, will that be, I think, would be good, I guess, yeah?
Yes, that's very true. Actually, in optics, we have a different domains to do this multiplexing, and each time we use multiplexing, we open the possibility to improving, in this case, the computation power. And I think that to put it like that, the real thing to address here is how can you do the wavelength separation, the routing prior to getting to the gates, if you want to do it like that, or if you want to process them separately, or if you want to process the information from different wavelengths by the same gate, that can also be straightforwardly be done. And one of the things, for example, that we think that could could help is to in the programmable processors, for example, one of the external blocks is to include a WDM demultiplexer, because that will allow you to enter the chip with a broadband with WDM source. And then, of course, you can program the waveguide mesh as an initial switch, so you can direct selected wavelengths to selected parts of the chip to do different processing operations. That is in principle possible, but it's just been the subject of speculation so far.
Yeah. So yeah, that's from my side. I think
there's one from Kumar that just wants to add to this discussion. So we hear a lot of new results based on non-volatile phase shifters based on GST materials, which seem to be quite a bit faster, and they've shown to be sub-microsecond or nanosecond scale. Will those kind of phase shifters be useful in this application?
Yes, I think yes, and we collaborate with a company called Lumiphase in Switzerland. They're doing this kind of non-volatile with BST materials, and they bring two advantages. Okay, the first advantage is that the power consumption is very low, as you can imagine, because there are non-volatile schemes. So once you set your current, your voltages, sorry, then you don't need to consume any energy until you, of course, until you need to change the state. I have to say, however, that thermo-optic phase shifters, the last generation of thermo-optic phase shifters do consume around 1 milliwatt per pi. So this is an astonishing low value. Of course, it's thermo-optic, so it's high if you compare with non-volatile. But this has gone down by almost 2 orders of magnitude during the last 4 years. So in that sense, in the sense of power consumption, non-volatile is okay, but phase shifters, thermo-optic phase shifters are pushing high, pushing strong. The other thing is probably more important, the switching speed. Okay. And some non-volatile, these materials, if they are able to recover from the crystalline to the amorphous, and this can be tamed, then this is an ideal. It is an ideal phase shifting mechanism. Though right now the phase shifters are, I mean, in order to achieve some noticeable phase shift, they are still long. But I think that can be reduced as well.
Yeah, just one more question from my side. You are always saying that this thing can be complementary. It cannot. It is not just competing digital computation. That I also agree. But what about comparison to quantum computing? People are talking because quantum computing is, technologically a lot of hardships are there, like single photon detector, low temperature operation, etc. Here you can enjoy room temperature detectors. So is it going to kill quantum computation, quantum photonic computation, if this somehow it stands up?
Well, I don't think it would be a way to leverage on photonic technology. The way that we have conceived this is to find a way of doing computing that is especially suited for photonics. Then quantum computing, in my opinion, has a lot of things to overcome, and I may be retired, by the way, by the time they are more or less addressed, but you very well mentioned the single photon, the room temperature. There are many more, like, for example, the decoherence, how you isolate your systems, how do you tame and you program your qubits? Because the things that have been demonstrated are really very, very basic operations where you really don't need to do a lot of programming. I mean, how do you program these these devices? For me, is a mystery, you know.
Yeah.
And I think it's a very interesting technology, but I think it's been we have very high expectations on being successful in a very short time period, and I think this is going to be extremely hard. I'm not saying it's not possible. I'm saying it's very, very hard. There are so many things that you have to how do you say, to fulfill, so many challenges that you have to address, that whenever you have something similar made of classical that you can go and put on a shelf and works, it's gonna bring later to a later stage the inception of quantum, because there are many things to be solved. I'm I'm not saying I'm skeptical. I'm not skeptical because I'm a scientist, so I have a very open mind. Okay.
Yeah.
But I think it's not going to be so fast as people claim.
All right.
Okay.
Thank you. Does any of the panelists have any questions? Arnav, Deeptashri?
It was a great talk. I just want to ask, like, if there is any special you need to take care about this heat management issue. Lot of phase shifters have to be there on the chip.
Yeah, good question. I don't know if Daniel had the time to talk about this, but actually we do in the lab also and in the company. We have developed different algorithms that we can use for first for monitoring, because don't forget that you have this is always a photonic chip, so you always have to monitor the state, because you know, temperature, crosstalks, etc. So all these individual elements have to be monitored. They have to be compared, and if you need a corrective measurement, even if you don't want to reprogram it, just to take care that they don't drift, you need to drive them or keep some kind of and of course you can say, okay, but these chips are very complex, so they can have like 500 elements. Okay, so we can do that. Yes, there are algorithms that can optimization algorithms. People like to call them machine learning, but for me, they are not really machine learning. They are very good optimization algorithms where you can select the cost function and really decide what you want to do with what you want to prioritize when you do the control. So the problems that we encounter in these chips are, first of all, to keep them in the right bias, to track the changes. Then what happens if you want to set up a circuit, which is the best place in the footprint to implement it, which will result on the less power consumption, or probably on the shortest path or whatever. For that, we exploit in the cost function different weights where we actually take into account what we, as I said, what we want to prioritize, what is important for us. And but I can say, not mistaken, that we can actually control over 500 elements simultaneously. So that's quite a lot. But again, you need also to miniaturize other things like the current sources, etc. And there's another evolution path on that we are working, but we and other groups, of course. And I think that will be sorted in that's an engineering problem, but there's not a fundamental limit on that. It's hard work, but it's not impossible. It's not like quantum, you know. It's doable in months or a couple of years time scale.
Yeah.
Thank you. Anything else? I have one question, because this is the first time I'm hearing about this concept called ANBIT. So I'd like to get in my head what exactly this ANBIT is in terms of scaling laws. So we talk about classical bits, right? They have 0 or 1. And then we talk about quantum computing having the scaling benefit, which means that a single qubit can hold both 0 and 1. So it scales as n rather than 2 to the n bits for the computation that you need. Does the AND bit fall somewhere in between, or do I see it as a classical bit itself in terms of complexity and scaling? How exactly should I view this AND bit concept?
Very good question. The AND bit is up to a certain point similar to a quantum bit. Okay, so actually you have like a superposition. Okay, you have, remember, you have amplitudes that multiply two vectors. Okay, you could think about these two vectors about being the 0 and the 1. Okay, and when you represent them, when you represent the state as it's being processed, that means at any time where you don't have to detect it, you can always think about this state as a wave. Nothing prevents you from doing that. And that's why actually it works, because you do interference, you do everything there. But at the end of the day, when you have to detect it, then you have to transform it into a particle. So you have to either select if you are going to go to one pole in the Bloch sphere or to the other. Once you have detected all the possibilities in your Bloch sphere, either materialize into the North Pole or the South Pole. There's nothing more than that. So you say, okay, in the meantime, I can do many things. I can play with that, but at the end, I only have a 1 or a 0. Okay.
Right.
The ambit is different. You can manipulate it as a wave, yeah. But then, when you recover it, you recover the amplitude and you recover the phase, and that means that you can recover any state in the sphere, not only the North Pole or the South Pole.
Right.
So the possibilities to carry information are much higher than the digital bit and probably than a single qubit, because you really can access to all these states in the Bloch sphere, because you are not destroying the wave when you detect it. Okay, you get the phase and the amplitude information.
Right.
So that opens.
Yeah.
Unexpected.
Yeah, sorry, Vijay seems to be having a follow-up. So I'll let you. Yeah.
I think let's finish Professor Kapmani.
Yeah. Kapmani, are you done, or do you have more to add?
It's fine. Just say thank you to all of you for your attention and for your.
No. In terms of the question,
I have one
response
more
to the question, sir.
Last curiosity, Professor Kapmani. So,
yes.
You have just explored everything using this unitary operation or non-unitary operation like Magenta interferometer. But for compactness point of view, have you explored that ring resonator kind of add-drop type things also can be used such operation? Have you explored that, and you find that Magenta would be the best? Just for curiosity, whether you have explored that or not.
Not yet. No, I haven't explored that.
Okay. Okay, fine.
Right. Thank you very much for patiently answering all our questions. We've gone well after our allotted time, I think. So, yeah, I'll probably hand over to Vijay and later to Diptashree to wrap things up.
You can go ahead for vote of thanks probably, and then we can conclude. Yeah.
Thank you, Professor Kapani, for this beautiful presentation and clearing all the doubts very briefly. And thank you, Professor Sudarshanan, for handling our Q&A session very nicely. And my heartfelt thanks to all the participants. And our next webinar will be on 4th May. So hope to see you all again. Have a nice day.
Thank you very much. Thank you all. Thank you,
Professor Kapani.
Thank you.
And take care, all of you.
Yeah.
Nice to see you.
Take care. Bye-bye.